All right, guys. Tonight we're going to look at how magnetism and centripetal force go together, especially with moving particles go with their magnetic field. Now, first off, let's actually look at why this relationship occurs. So I'm going to have a magnetic field going into the board, uniform magnetic field, so it's evenly distributed, and let's consider it to be infinitely large. Infinitely large. In other words, whenever we shoot a charged particle into it, the particle is never going to run out the other side. It's going to always be in this magnetic field. Okay, we're never gonna lose it. Right now, we had talked about how electric generators and electromagnets and all that is formed. It comes from the idea that when a charge goes through a magnetic field, right, there's a force applied to it, and that gives us our idea of an electric motor, right? And that's kind of the idea behind everything. So a force is applied to a charge that goes through it, and that derivation gets us to all of those electromagnetic devices that we kind of briefly talked about. We're going to continue to explain more of in class. But anyway, now there's this odd effect, right? Whenever we shoot a particle, let's take an electron here, right? There's this odd effect whenever I shoot an electron. Actually, I don't want to use an electron. Let's use a proton here. Let's use a proton instead. A charged particle, it really doesn't matter what it is, but let's say a proton into a magnetic field, right? A force is applied. The way we figure out the direction of the force is using the left-hand rule, left hand for positive charges, right? You can either remember that if it's negative, you just reverse the direction of the force, or you use the other hand. Here, we're just going to use the other hand, but we don't have to since it's a positive charge. So right now, I've got this proton. Its velocity is towards the right, and the magnetic field is going into the board or into the computer screen. So taking my left hand to see which direction the force is going to be applied. Index finger always stands for magnetic field, and it's going into the board, so I'm going to point my index finger into the board, or for you, into the computer screen. Rotate your wrist, right? This is, remember, using the left hand. Rotate your wrist around to where the other fingers are pointing to the right, the same direction as the velocity of the particle. Stick your thumb up, right? Stick your thumb out. It's pointing straight up, which indicates to us that the force this particle feels whenever it's at this point is up, like that, right? Now, let me take you to a idea that you're already familiar with here, to try to think about what type of motion this is going to be. Specifically, this. It's got a cliff that is 120 meters high, right? A object, rock, ball, box, whatever you like, is thrown off horizontally, straight off some velocity. This box, if it's just thrown straight off and it goes through free fall, only has a single force acting on it if we neglect air resistance, and that's the force of gravity. And the force is at a right angle to the velocity. And so what motion do we get out of this guy? Well, we get an arc, right? We get that. Okay, we get an arc out of it, where in the beginning there isn't much velocity gained in the y-axis. We're talking about here. Okay, not much velocity in the y-axis. That's why it hadn't fallen far at first, but has gone a lot farther in the x-axis. But the force of gravity, it picks up steam, right? I mean, it's accelerating the object. So the velocity becomes larger and larger and larger until it pulls it to, if it's high enough, almost going straight down. Okay, so whenever a force, the entire point behind us, whenever a force and a velocity, an initial velocity, are at right angles to each other, right? What's going to occur is an arcing motion. What's going to occur is an arcing motion. So here, what's going to happen is my proton is going to move in an arc. Okay, in an arc. Till it's, over here. It's proton plus. Okay? Moving in an arc. Let me extend my magnetic field where we can really see what's going on here as we continue this idea. Okay? All right, that should be good enough. Now, over here, we've arced the proton around until it's over here now in the magnetic field. Now, its velocity at this point in time is going straight up, right? It's going straight up. And the magnetic field is still going straight in to the board, right? Straight into the board. They're at 9 degrees to each other. So let's use left-hand rule still, and let's figure out which way the force is going to go. So positive, left hand, take my index finger, point directly into the board, rotate my fingers around, my other fingers around, so rotate the wrist where the other fingers are pointing straight up. For you on your computer screen, index finger going into computer screen, other fingers going up. Stick out the thumb, and the force that this proton is going to experience is going now to the left. Now going to the left. Well, here we are again, right? Force and the velocity, right? The force and the initial velocity are at right angles to each other, which is going to give me a arcing motion, right? An arcing motion. Now here we are. Let's take it at the top of this kind of semicircle, if you will, up here at the top, right? At this point in time, the velocity is going to the left, right? And so let's figure out which way the force is again, right? Magnetic field goes into the page or into the board. Velocity now is going to my left, so rotate my wrist around, stick my thumb out. I find the force is going to go down, right? So like this, and so we have another arc on around. So right here, and you can probably already guess what's going to end up happening. The initial velocity is like this, coming downwards for my proton, which, whenever I use left-hand rule, is going to give me a force pointing like that, which is going to give me another arc. And you can already see what's happening here, right? I have a circle. I have the proton making a circle with the force always pointing to the center. Always pointing to the center. This is the definition of centripetal force. Now we actually use this this idea for making charged particles go in circles whenever we're trying to create fusion. So we take hydrogen, generally, take hydrogen gas, and we start heating it up. The way we keep it from hitting the sides is by magnetism. We get it spinning really, really fast in a torus, so that we can keep it from flying all out. See what happens. So we're not to a point we can obtain fusion. We're just not to a point where we get the same amount of energy out from the fusion as the amount of energy we put in to actually make this happen. But we're getting a lot closer. Kind of the idea behind fusion. We'll get to this with the nuclear section. The idea behind fusion is it's clean nuclear energy, right? Two hydrogens come together and give you a helium. Nothing radioactive about that at all. It's clean energy, and incredibly efficient too. But we're not there yet. But this is kind of the idea of where that has been. But anyway. Put a charged particle in a uniform field if you allow the field, if the field is large enough, and if you allow the particle to continue its own natural motion, it's going to go in a circle. It's going to give me centripetal force. So now what this tells me, I'll clear away a little bit of this field to where we have on the right. What this tells me is, right, you always start with the centripetal force equation, mv squared over r, and then your next question is, what are the sum of the centripetal forces? Here, there's only one, right? It's this magnetic force, right? It's this magnetic force. That's what's causing the particle to go in a circle. The left-hand rule idea, right? That's what's causing it to go in a circle. Well, charged particle moving in a field, we have an equation for that. Q, V, B. And I'm going to leave off the sine theta here. I guess I'll write it now, sine theta, but we want theta to be 90 degrees, right? We want theta to be 90 degrees. Sine of theta is 1, so this goes away, and I get QVB equals mv squared over r. Okay? QVB equals mv squared over r, where the left-hand side, QVB, is the magnetic force, right? And the right-hand side, mv squared over r, is the centripetal force part. So this force, the magnetic force, QVB, is what's causing the particle of mass m to go in a circle at a tangential velocity v and radius r. Okay? And you can probably already see how we could divide velocity on both sides to get one of those velocities to cancel out. I'm not going to worry about that right now. This is the concept right here. Now, is this a master equation that you could write down? I guess if you really wanted to, but really it's just the magnetic force equals the centripetal force. It's just this centripetal force concept we've dealt with so often, right? I mean, heck, we can plug in normal force and gravity, whether it be added or subtracted in there for a roller coaster problem. We can plug in Coulomb's law if we're dealing with an electron going around a proton. I mean, all sorts of things can go in there. Universal gravitation for planets going around the sun or anything like that. Moons going around a planet. It comes from the centripetal force side. Anyway, a couple of example problems here for you. An electron is shot into a 45 MT here, that's Tesla, is the capital T part. The little m stands for milli, so I'm already thinking 45 times 10 to the negative third Tesla, because that's what milli stands for, negative third. All right, shot into a magnetic field perpendicular, thank goodness. I don't have to worry about sine of the angle at a velocity, right? What is the radius of the path the electron takes? Now, I'm not going to redraw this because the picture is the exact same thing. Actually, I do want to redraw it now that I'm thinking about it. So I have a magnetic field, and I won't give myself this many circles and X's in it. We'll make the magnetic field go into the board again. All right. So whenever I shoot an electron in, right, E negative, whenever I shoot it in, it's going to go in a circle the opposite way, right? Negative, right? That means the force is being applied in the opposite direction. I'd want to use my right hand here. I'm going to get a circle where the electron goes like this, clockwise. Whenever I was using positive particles, with the magnetic field going into the board, it was going counterclockwise, right? All going around this way, right? And coming back around counterclockwise. Here with the negative, it's going clockwise. Now that what I just told you, that rule of thumb, only works with magnetic fields going into the void. The main thing you've got to take away from this are positive and negatives, at least from this little bit. Positive and negatives will go in circles in opposite directions. They're going to orbit in opposite directions. One goes clockwise, the other's going to go counterclockwise. Okay, that's because the force is opposite on each of them. Anyway, this is really just a plug-chug problem, right? Sum of the centripetal forces equals mv squared over r, and I can leave off the sine theta. This just becomes qvb equals mv squared over r. Okay, we know pretty much everything here. The charge of an electron, 1.6 times 10 to the negative 19. And I'm going to leave off the negative sign. That negative sign with math here, remember, deals with direction. And I have dealt with direction myself manually. I've drawn a picture, I know what's going to happen, right? And what I'm looking for, the radius, right? I don't need a direction on that. It's just a distance, not a displacement here. All right, so 1.6 times 10 to the negative 19 times 0.08 c. 0.08 c, by the way, c, speed of light, right? 3 times 10 to the 8 meters per second. But I'll plug that in later since I'm probably going to run out of space here. Let's see if I can move all of this, or at least most of it here. Let's move that. And then let's move all of these over here. Try to give myself a little bit more room. Times the magnetic field strength, 45, times 10 to the negative 3. Okay? I'm going to go ahead and write it C for you. 3 times 10 to the 8 meters per second. So it would be 0.08 times 3 times 10 to the 8 equals mass of an electron, 9.11 times 10 to the negative 31st. Here's that velocity again, 0.08 c. That quantity is squared. Sorry for writing on top of the picture there. I know it can get confusing. Divided by the end goal, the radius. Let me work this out just in letters for you. I mean, here you would do the algebra, right? I'd multiply the radius to the other side, and I'd take everything on the left-hand side and divide it over. In other words, in letters, I'm going to come out with R equals mv squared divided by qvb. And so, as you can see, one of the velocities would cancel out if I so chose not to do this in actual numbers. Anyway, so then we plug that into our calculator, and we come out with the radius. All right, so I come out with the radius of 0.00303 meters. Or if I had to do that, that would be 3.0 millimeters, and a very short radius here for this strong magnetic field, right? It's going to cause that electron to bend around pretty quick. Now, let's go back and let's do the exact same thing with an alpha particle. Now, yes, the alpha particle will rotate a different way because it's a helium nucleus. That means it's positively charged, but it also, that's not the part we care about, right? We care about the radius here. Which means it's really just the math, right? The radius we said from the previous idea, and here we actually work this through again for you. Sum of the centripetal forces is mv squared over r. Well, what's causing this alpha particle to go around in the circle? It's the magnetic field, right? Q of VB equals mv squared over r. And then solving around for r, right? R is going to give me mv over qb. Remember, I canceled out one of the velocities here. So then I can plug in numbers for this and get the radius. Now, let's actually go through plugging in numbers to show you that the mass of an alpha particle is different, right? An alpha particle is a helium nucleus. It has 2 protons, so 2 times the mass of a proton, 1.673 times 10 to the negative 27 plus 2 neutrons. Okay. By the way, all these masses can be found in that constant sheet I gave you. 1.675 times 10 to the negative 27. All that's in kilograms, of course. I'm running out of space, so let's see. Take this and try to get up and move it over a little bit here. And then that's times the speed of 8% the speed of light, 8.0 times 310 to the 8, right? 8% times the speed of light. All divided by the charge of a helium nucleus. Well, the only particle inside a helium nucleus that has charge are the 2 protons. So 2 times the charge of a proton, which is once again 1.6 times 10 to the negative 19, the elementary charge, times the magnetic field strength, which was 45 millitesla, right? So 45 times 10 to the negative 30. Plug that all into our calculator, and we get the radius of the alpha particle. All right, we come up with a radius here of 11.16 meters with 2 sig figs. That's 11 meters. And you can see the huge difference between the radiuses, right? 3 millimeters compared to 11 meters. The radius, they're just so different, mainly because of the mass of the particles, right? I mean, think about it. The alpha particle is so much bigger, times 10 to the negative 27. I understand that's a small number, but compare that to times 10 to the negative 31st to the electron. That is a much larger thing that has to be turned. I mean, this is this entire radius is many times larger. In fact, it's over 3,500 times larger just due to the fact of the differing masses. Yeah, there's a little bit extra charge, but that really doesn't play as big of a factor as the mass. So anyway, I'll check this again on Monday, of course, so make sure you have good notes on it, and then we'll work a few problems with it.